All right, so in this video, we're going to prove a proposition about paths in Rk, which just says that a path is continuous if and only if its component functions are all continuous, much like the lemma that we proved in section 13 about, or in lecture 8, I guess, section 13 in the book, about convergent sequences of points in Rk. That where the lemma stated, if you remember, that a sequence of points in Rk is convergent if and only if the component sequences are all convergent. So this is actually, it's very closely related to that. I'll say a few more words about that at the end. So let me state the proposition. So this is 21.2. So let gamma be a function from the closed interval AB to Rk. And we're considering the closed interval here just because that's kind of the most common scenario that we're like interested in practice. And things can get weird if the domain of gamma is not compact. So if you let gamma be all of R, or if you let gamma be an open interval or something, then strange things can happen. So I mean, I think the proposition will still be true, but we'd prefer to just not worry about that, and we'll just consider the closed interval AB. So gamma is a function. So say gamma of t. So we're going to give names to the component functions. So f1 of t, f2 of t, f3, or well, yeah, you get the idea. Fk of t. These are the component functions. Then gamma is continuous. Let's say gamma is continuous, i.e. a path. So we only call gamma a path in this case if it's actually continuous, okay? So if you just have a random function from AB to Rk, that's not going to be called a path. So that's kind of why we're not considering continuity at a point either, is just because if you only required gamma to be continuous at one point, it wouldn't be called a path. So we want to think about gamma as a path. Not that it matters for the proof, but it's just that that's what we're interested in analyzing, or at least would be if we were going to talk much more about this. So gamma is continuous on AB if and only if fj, the function fj is continuous for all j, j going from 1 to k, right? So, okay. The proof here relies on the same inequalities from lemma 13.3, I think. So we have this inequality, right? Xj minus yj. For 2 points in Rk, we have this. Oops. Right. This was what we talked about in lemma 13.3. Just to refresh your memory, right? Because the expression for this is, x1 minus y1 squared plus all the way up to xk minus yk squared. So to go this way, right? Or well, the easier one's this one. So to go this way, all you have to do is imagine, for any given j, this is true for all j, right? Of course, this side does not depend on j because this maximum here is just one quantity. It's just one number. The j is inside of this, between these brackets here, so it doesn't, you can't really talk about it. This is just one number. But this, you could let j change and you'd get different numbers here, but they're all bounded above by this. And the reason for that is that if you're given any j, if you just delete all the terms inside the radical here, except for that jth term, then you would end up with the absolute value of xj minus yj. But of course, that has to make the value smaller, because if you're deleting all these terms, those are all positive terms. So that has, by deleting them, you'd be decreasing the value, right? So then on the other side, it's just, if you were to just take all of these terms inside and replace them by whichever one is biggest, right? Then you'd get k times the biggest, like xj minus yj squared. But then you could pull the xj minus yj squared out of the radical, and you'd end up with square root of k times whatever that maximum absolute value of xj minus yj is. Okay, so that's where these inequalities come from. And basically, the proof is very similar in structure to that for 13.3. So I'm going to go through it fairly quickly here. So first, we'll just suppose gamma, or let's see. Yeah, we'll suppose gamma is continuous first. So suppose gamma is continuous. And we want to show fj is continuous, all j, right? So let t naught be point in AB. We'll show that fj is continuous at t naught. So let epsilon be greater than 0, right? Then, so given epsilon, since gamma is continuous, there exists a delta greater than 0, such that for all t in AB with t minus t naught less than delta, we have that the distance between gamma of t and gamma of t naught is less than epsilon. That's by definition of continuity for gamma, right? So then, because that's true, we automatically get that for all t in AB with t minus t naught less than delta, we have fj of t minus fj t naught absolute value is less than epsilon because of the first inequality, right? Because of this inequality, this is true for all j, because this is less than or equal to this, which is in turn less than epsilon, right? So that shows that fj is continuous at t naught, which was arbitrary, right? On the other hand, suppose fj is continuous on AB for all j. Let t naught be a point in AB, and let epsilon be greater than 0 again, because now we're trying to show that gamma is continuous, right? So then there exists, so for each j, right? Now, because we're assuming that we have k different continuous functions, one for each value of j. So for each j, select delta j such that for all t in AB with t minus t naught less than delta j, we have absolute value of f of t minus f of t naught, fj, sorry, fj of t minus fj of t naught is less than epsilon over square root of k. And that's just for later. Okay, but so epsilon over square root of k is just a constant, remember, because k is the dimension of the space. So epsilon over square root of k is just some constant. So we can force fj to be within that constant distance away from t from fj of t naught, because fj is continuous. Okay, so by choosing delta j, we can do this. So then take delta to be the minimum of delta j, right, of all the delta j's. Then for t in AB with t minus t naught less than delta, we have So this means, so if t minus t naught is less than delta for this choice of delta, then t minus t naught is less than every delta j, right? So that means that every one of these inequalities is satisfied for every j, right? Because t is actually less, t minus t naught is actually less than each delta j, right? So for that value of t, absolute value of fj of t minus fj of t naught is always less than epsilon over square root of k for every value of j. So that means that the maximum one of those values is less than this thing. So the maximum of these fj of t naught minus fj of t, I flip the t naught and t naught, it doesn't matter. This is for j equals 1 to k, is less than epsilon over k, sorry, square root of k. So by the inequality that we said before, this means that the distance between fj of t and fj of t naught is less than square root of k times epsilon over square root of k. So that's epsilon. Excuse me. So that's all we wanted to show. And that concludes the proof. So gamma is continuous. And one kind of interesting thing that I'll say just to cap this off is that actually this proof would have been effectively trivialized if we had taken as our definition that that sequences, if we had taken the sequential version of the definition of continuity, if we had generalized that sequential definition to metric spaces, then we could just adapt Lemma 13.3 directly to the proof of this fact for that definition of continuity. But then, of course, we would still be left with the task of eventually showing that the sequential definition of continuity for metric spaces is still equivalent to the epsilon delta definition of continuity for metric spaces. So it's sort of a, a trade-off, I guess. But this proof would have been unnecessary. It would have been more or less, basically like two lines or 2 or 3 lines if we had used the sequential definition of continuity for functions between metric spaces. Okay. So anyway, maybe think about that. It's, it could be helpful to reinforce your knowledge. Okay, so in the next video, I'll talk about the topological characterization of continuity, which involves looking at inverse images of open sets. And it's a very, very beautiful topic. And I think it's one of the most important ideas that we'll cover in this class. So yeah, that's it for this video.